Welcome to the course on error control coding and introduction to linear block codes. So, in the last lecture we discussed about bounds on the size of the code. Now, let us solve some problems related to that. So, the first question is it possible to have a linear block code, binary block code, which has n given by 16, k given by 10 and minimum distance of 8. So, when I write this like this, this stands for n, then this is k and this is minimum distance. So, is it possible to have a code which has length 16, information sequence length 10 and minimum distance of 8? Now, how do we solve it? We have talked about various bounds on minimum distance. So, let us see whether this satisfies the bounds on minimum distance. So, let us start with singleton bound. Well, the answer to this question is no. The reason being, for example, this does not satisfy the singleton bound. Now, what is singleton bound says? The minimum distance of a code has to be less than equal to n minus k plus 1. Now, n here is 16, k is 10 and this is 1. So, what singleton bound says that minimum distance of a 1610 code cannot be more than 7, and here we are saying minimum distance of 8. So, that means it is not possible to have a linear code with these parameters. Now, please note, whenever such questions come, you will have to check whether all the bounds on minimum distance are satisfied or not. The next question is 24, 12, 8 binary Golay code, is this a perfect code? Now, again here n is 24, k is 12 and minimum distance is 8. Now, what is a perfect code? A code that satisfies Hamming bound with equality is a perfect code. So, we have to check whether this code satisfies Hamming bound with equality. The answer to this question is no, and we will come to that in a minute. It does not satisfy Hamming bound with equality. So, what does Hamming bound says? If you have a binary nk code whose minimum distance is 2t or greater, then number of parity check bits must satisfy this constraint, and codes that satisfy this inequality with equality are known as perfect codes. So, we will have to check whether this 24, 12, 8 Golay code satisfies this Hamming bound with equality. So, the minimum distance is 8. Now, what would be the error correcting capability of this code? So, this will be d min minus 1 by 2 and floor of that. So, in this case it is 8 minus 1 by 2. So, this is a triple error correcting code. 24, 12, 8 Golay code can correct 3 errors. So, T for this code is 3. Okay. So, let us just compute the right hand side, this one. So, this will be 1 plus n is 24, 24 choose 1, 24 choose 2 plus 24 choose 3, because t is 3. So, this is 1 plus 24 plus 276 plus 20, 24. So, this will be 2325. So, the term that we are getting on the right hand side is 2325. Now, let us look at the left hand side. This is 2 raised to the power n minus k. So, n is 24, k is 12. So, this will be 2 raised to the power 12, and this is equal to 4096. Now, note left hand side is greater than right hand side. Left hand side is 4096, right hand side is 2325. So, this particular code does not satisfy Hamming bound with equality, and hence it is not a perfect code. Next, if we are given a linear block code C, let us just say an NK linear block code, and it is said that this code is maximum distance separable, then show that its dual code is also maximum distance separable. Now, what do we mean by maximum distance separable code? We know the codes that satisfy singleton bound with equality are known as maximum distance separable code. So, then if this NK code is maximum distance separable, then the minimum distance of this code should be n minus k plus 1, right. This follows from the fact that our given linear block code C is maximum distance separable. Now, if the minimum distance is n minus k plus 1, it means that there are no n minus k or less columns in the parity check matrix of this code which are linearly dependent. If you recall, the minimum number of columns of this parity check matrix which are linearly dependent basically can be found out from, if we look at various, if we add up the columns of the parity check matrix, the minimum number of columns that add up to 0 is the minimum distance of the code. Now, if the minimum distance of the code is n minus k plus 1, it means no n minus k or less columns of this parity check matrix will add up to 0. So, that is what we are saying, no n minus k or fewer columns of this parity check matrix are linearly dependent. That is because the minimum distance of this code is n minus k plus 1. Now, let us look at its dual code. Now, what do we know about the dual code? We know that the generator matrix of a dual code is same as parity check matrix of the original code. So, for this dual code then H will be the generator matrix. This follows from the property of dual code. And we also know the dual code word length should be n, and since this was an NK code, the dual code dimension should be n minus k. Now, to prove that this dual code which is specified by these parameters length n and dimension n minus k, to prove that this is maximum distance separable, we will have to show that its minimum distance is given by d min is equal to n minus dimension is n minus k plus 1. So, we will have to show that minimum distance of the dual code is k plus 1. So, that is what we are going to show now. To prove that the dual code is maximum distance separable, the dual code also has to satisfy singleton bound, and according to singleton bound, the minimum distance should be n minus dimension of the code, which is n minus k plus 1, and this comes out to be k plus 1. So, we will have to show that the minimum distance of the dual of this code is k plus 1. Now, to prove this result, we will take help of what we call method of contradiction. So, how does the method of contradiction work? We will start off with the assumption that there exists a code word of weight less than equal to k. So, we will assume that minimum distance is not k plus 1, and then we will show that through the properties of this code that this condition is not possible. So, our assumption that there exists a code word of weight k or less is incorrect, and hence the minimum distance should be more than k, and then we will use singleton bound to show that minimum distance can at most be k plus 1, and hence the minimum distance of the dual code is k plus 1. So, this is the approach that we are going to follow. So, as we said in method of contradiction, we will first assume that, let us assume that there exists a code word of weight less than k plus 1. So, we assume that there exists a code word v of weight d prime, which is less than equal to k. Now, if there exists a code word of weight less than equal to k, what does it mean? That the code word v will at most have k once, right. So, our code word v is a n bit code word. So, out of this at most k bits are 1, so remaining n minus k bits are 0. So, we can at most have k once and n minus k or more bits are 0. Without loss of generality, let us assume that those bits which are 0 are towards the end. So, what we are assuming is, let us say this is our code word v. So, first k bits have 1s and these remaining bits have zeros. So, these bits have zeros and these bits have 1. Okay. Let us assume that. Now, the parity check matrix of the original code, which is the generator matrix of our dual code, can be written in this particular form. Now, please note this parity check matrix is n minus k cross n matrix. So, this I am writing as one matrix, which is A matrix n minus k cross k, and then there is an invertible matrix which I call H prime, which is n minus k cross n minus k. Now, what was the rank of this matrix H? Remember, we have, because minimum distance of the code was n minus k plus 1. So, no n minus k or fewer columns of H were linearly dependent. So, the row rank was n minus k. So, column rank is also n minus k. What does it mean? It means that n minus k, there are n minus k independent columns in this matrix, and let us say those n minus k independent columns are this, given by this H hat. Okay. So, this is since this has independent column, this can be inverted also, and rows of this matrix H hat is also independent because it has rank n minus k as well. Now, remember what did we say about our code word v? We said our code word v, the first k bits, at most first k bits are 1. So, these first k bits can at most be 1 and these are all zeros. So, remaining n minus k bits are all 0. Now, this H matrix is the generator matrix. This is a generator matrix for dual code CD. So, if we have to generate a code word like this from this generator matrix given by this, we will have to use this matrix. Now, remember, to get 0 in the last n minus k coordinates, now this consists of n minus k linearly independent columns and rows. Now, to get 0 in last n minus k coordinates, the only way we can get it is if we use a 0 linear combinations of all rows. So, if we do 0 times all the rows, that is the only way we can get this condition. Why? Because this is, remember, this is a linearly independent columns and rows. So, only ways we can get all 0 here is if we take 0 linear combination. So, we multiply all the rows of this generator matrix by 0. But if we do that, what is the minimum distance that we get? If we do that, the code word that we get is all 0 code word. So, what it means then, that our assumption that there exists a code word of weight up to k is incorrect, because we are not able to construct that code word using the generator matrix of the dual code. Hence, our assumption that minimum distance of the code, there exists a code word of weight less than equal to k was incorrect. So, we can conclude or say that the minimum distance of the code is at least k plus 1. Okay. Now, how do we show that it is exactly k plus 1? Now, we know that minimum distance of the code must satisfy the bounds. Now, it should satisfy, for example, singleton bound. Now, what does singleton bound says? Singleton bound says minimum distance of the code is upper bounded by n minus dimension of the code is in this case n minus k plus 1. So, from singleton bound we get the condition that minimum distance should be less than equal to k plus 1, and from this we get the condition that minimum distance is at least k plus 1. So, if we combine these two, we get the condition that minimum distance of this code is k plus 1. Hence, it is proved that the dual code is also maximum distance separable, because it satisfies singleton bound with equality. With this, we conclude this lecture. Thank you.